So let's just pick up where we left last week, I think, if I'm not wrong. So last week I introduced to you the potential flow. I think this will be a good point to just to revise. So we know now there are two functions, stream function psi and the velocity potential phi. Hello? Right, what we said is the stream function is basically can be used to describe the streamlines. And the basic understanding is that if you have a flow like this over an airfoil in 2D, okay, then each streamline will have a constant value of stream function psi. So, for example, if we consider these two streamlines above each other, the first one will have psi 1, which is constant. Let's call that C ref. And this second one has, as we go up, the value of the stream function will change by a certain amount, and we call that the stream function psi 2 here equals C ref plus a small amount delta psi. And if you actually, when we think about it physically, that change in the stream function between two streamlines, it turns out is the same as the volumetric flow rate going through them. Okay, that's physically what it is. Now, in terms of velocity components, I've shown you this already, so very quickly, the velocity component in terms of psi is u d psi dy, and v is minus d psi dx. That's how you get. So this means if I know what the stream function is, I can actually work out the u and v, right? That's the main thing to remember. If someone gives you the stream function, you can work out the velocity field. So be very careful with the signs. We also spoke about the velocity potential phi, so this is a quick revision. Similarly, we can also express the velocity components u and v in terms of phi. So if you know phi, you can work out u and v. So u is d phi dx, v is d phi dy. And here it says note the signs. So also note the definitions. They're slightly different. Don't confuse them. And from before, they satisfy the Riemann equations, and we can get a complex potential function w out of phi and psi. So I'm not going to repeat myself there. I've already spoken about this. So what's the relationship between these two functions? Well, they are actually orthogonal to each other at 90 degrees. Whenever they cut each other, they are actually at 90 degrees. So if you get a flow with streamlines like this, so if you guys think about the blue lines as the streamlines, because I told you the streamlines basically are defined by lines of constant stream function. So the blue ones are streamlines, and if you draw the velocity potential lines across them, they will be always at 90 degrees. Now, incidentally, those potential lines, they're called equipotential lines sometimes, if they are, well, because they link the same phi everywhere, they can call them equipotential lines. The main thing is they are at 90 degrees to the stream function. So psi and phi always at 90 degrees. What we also said, that unlike the stream function, which you can actually work out for a wide range of flows, probably even unsteady flows, we can define stream function. What you guys need to remember about velocity potential, however, is that it's only true if the flow is irrotational. So if the flow is not irrotational, it's not possible to define phi, but it's always possible to define psi. Okay? So please remember that. I think that's where, okay, so let's just keep going on. I think we said this already. So both psi and phi satisfy the Laplace equation. That's the continuity equation I spoke about before. Okay, and what it means in terms of velocity components. Okay, what I'm saying here really, if you take the divergence of the velocity field, which must be 0 for incompressible flow, or the continuity equation, in 2D is written like that. In terms of phi, it becomes a Laplace equation that is equal to 0. So you can actually prove from here, if you substitute for u by d phi dx, it becomes d squared u phi dx squared plus, you will get 0. It's just you proving that phi satisfies the Laplace equation. Similarly, if you take the fact that the flow is rotational, so that means the curl of V is 0, delta times V is 0, the vorticity is 0, and you express that in terms of the stream function, then you also you can show that the stream function satisfies the Laplace equation. So this is just another way of showing you how you can prove that phi and psi satisfy the Laplace equation. From, first of all, the irrotationality, that's for psi, where the vorticity is 0, and secondly from incompressibility condition for phi. So that's the main thing. Phi and psi satisfy the Laplace equation. So, as I told you before, because they both satisfy the Laplace equation, okay, it's me and they are linear, we can actually add the solutions to get another solution. So you start from a solution that satisfies the Laplace equation, and there is another solution that satisfies the Laplace equation. If you add them together, that addition of two solutions is also a solution of the Laplace equation. And that's the kind of the practical advantage of the Laplace equation. So this brings me again just to stress the so-called superposition principle. So what I'm saying there is, if I have a function phi and a function phi1 and phi2, let's say phi1 and phi2, so phi1 satisfies the Laplace equation, phi2 satisfies the Laplace equation. What I'm saying by the superposition principle, which is just another posh name of adding, superimposing something, is that phi1 plus phi2 is also a solution. I hope you guys can see that. So if phi1 is a solution, phi2 is a solution, phi1 plus phi2 is a solution. That's basically addition or superposition. So in aerodynamics of potential flows, it means I can add simple flows together to get a more complex flows. Okay? So that's what it is. So that's the key concept there. For example, I will show you through these potential flow lectures that if I start with something called the source flow, which I know you don't know probably, the source flow, if you add a sink flow to it, you get something called the doublet flow. And out of the doublet flow, we can get something else. And it becomes really interesting where you can actually model some really interesting complicated flows out of simple flows. But remember, all of them, they satisfy the Laplace equation. Then if I take the doublet flow plus uniform flow, you can actually get flow around a cylinder, which is fantastic. So a cylinder is actually a very practical problem. I know it's a 2D problem, but in 3D is actually basically flow around, 3D pipe, for example, or a riser somewhere. So it's actually a very important problem. And you can get the flow described around the cylinder by combining something called the doublet flow and uniform flow. So in general, because these flows satisfy the Laplace equation, I can get flow 3, I call that flow 3, equals flow 1 plus flow 2. You can just add them together. And flow 3 will satisfy the Laplace equation as well. But as you can see, because you're adding two things together, for sure flow 3 is more complicated than only flow 1 or flow 2. Flow 1 and flow 2 are meant to be simpler. Flow 3 is more complicated, but it becomes more interesting because you're approaching more practical examples for flow 3. You can get flow 4, flow 5, flow 6, whatever. You can add things together to get really interesting practical flows. So that's the superposition principle. And remember, it's only possible because it satisfies all those simpler solutions that satisfy the Laplace equation. So we can add them together to get flows around bodies, okay, even including flow around wings and airfoils. So I just thought maybe just to kind of take you out and think about while we're talking about potential flow, really for us, at the end of the day, whatever we call this flow, whether it's full Navier-Stokes equations or the very simple potential flow, really, to be honest, at the end of the day, you want to know what the lift and drag is on your wing, right? You don't want to be lost in all these theory of potential flow. So just to give you an idea here so you guys don't lose the plot, is basically within potential flow, once we have solved for, let's say, the velocity potential phi. So I know what the velocity potential phi is, or you define it, okay? The flow is irrotational potential. Then out of that, you can actually get the velocity components from this definition, right? Very simple. So you know what the velocity component in the x direction u is out of phi, and what the velocity component v in the y direction. So now you know the velocity field. Well, you're not there yet. That's not the full story. But the good thing is, using the Bernoulli's equation, if you guys remember it from last year, or anyone remembers the Bernoulli's equation? Yes, what is it? P plus half rho v squared equal to a constant. Anyway, the Bernoulli's equation really links pressure and speed in one equation. Now you know what the speed is. Okay, you know what the speed is. From that, using the Bernoulli equation, you can work out what the pressure is. Now the pressure is very important because it leads to things like lift. And as I told you, this is really what you want. So, you know, out of all these potential flow, really, you want, for example, what is the lift over my wing or airfoil, right? So this is really generally how things work. So you start with a stream function or a velocity potential. Then you get the velocity components. From the velocity components, you use the Bernoulli equation to get the pressures. And from the pressures, you can integrate those to get things like lift. And this is how the solution works. So it's not like trivial. We just introduce you to potential flow. It's actually can actually give you some useful indications. And I think I touched very quickly last week on this one. This is really just, again, to reiterate what I've been talking about, how all these equations link to each other. So in 2D incompressible flow, that's the equation in terms of velocity components. And really, if you combine it with the stream function definition for velocity components, you can get something that looks like a Laplace equation. Okay, so it's consistent with the Laplace equation. But also in terms of vorticity, you can also make it consistent with the Laplace equation. So that's really just to show that everything is consistent within each other. Right. Now it gets a little bit interesting now. So far we've been talking about Cartesian coordinates. So simple in 2D, just x and y with unit vectors I and j. To be honest, if you were a mathematician, any of you are mathematicians, you're actually, in many cases, your life is a lot easier if you don't actually work in Cartesian. Now Cartesian is easier maybe to deal with. We're more familiar with it. But actually, in many cases, it's actually better to use another system. And one of them, for example, is what they call it, the cylindrical coordinates, and also there is the polar coordinates. Oh, spherical, sorry. So, in that system, instead of having u and v, which we know from Cartesian, we can get, for example, v of theta. So, in a typical cylindrical coordinates, you have the angle theta, and you got the radial direction r. And this is how you can express those velocities u and v. So, we will have v theta in terms of psi is this way, and in terms of phi is written this way. The other component, which was v, now becomes vr, which is a long r, and in terms of psi is written this way, in terms of phi is written that way. These are all very standard equations. I'm not inventing things here. That's just mathematics. Now, if you get lost, at least between Cartesian and cylindrical coordinates, what you really simply can remember is that the x in the Cartesian is just r cosine theta in a cylindrical coordinate, and y is r sine theta. And if you do that, you should be able to write the velocity components at least in cylindrical form. Okay, so don't be afraid if you see these sometimes written in something which is not Cartesian. It's exactly the same, and as I said, sometimes actually a lot easier. Okay, let's just keep going. Oh, all right. This is just one of Sean's ideas. Okay, so the question is, which flow is rotational and why. So you guys need to look very closely. So remember, rotational just means something rotating about an axis. Anyone? Yes, what? One in the left is what? Okay, why is that? So could you be more specific? So you know those, okay, give me a hint. Those white lines that goes with the balls, what's happening to them? On the in the red one, is there anything happening to them, or are they staying straight? But the blue ones, what about the blue ones? No, there is a bit of twist. If you look very carefully, they're twisting. Now you won't see it on the PDF. So Joe is actually correct, but I just want you maybe to look very carefully here. If you look at these lines here, that's kind of in the middle of the ball. You guys can see as they go around, they actually kind of twist a little bit, which means there is some rotation. Whereas the other ones, they just translate. There is nothing happening. But it's very difficult to say. It took me a while to realize that. But this is one of those typical half lecture something to distract everyone. Okay, let's talk about the concept of circulation. What is circulation? Circulation, guys, hello. Circulation symbol kappa is basically, by definition, is basically the integral or summation of the velocity field around the closed curve C. So if you take any closed curve C in space, and along that curve there is a velocity field that you can define. If you take the integral of that velocity field along that closed curve, that what will give you the circulation. That's the concept of circulation. Now, you know, we've been talking about vorticity and stuff. This is a new concept now. Okay, so you got a closed curve C. Okay, as I said, there is a velocity field associated with it. If you take the integral of the velocity field along this curve C, you get circulation. We can also use, so that's by definition, we can use something called the Green's function theorem, which allows us to write this line integral. Now remember, did you guys see this in maths? Where if yeah, do you see that in maths? Or so this just means it's closed. This circle here just means I'm going around a closed loop or a closed curve. So as I told you, so that's the integration of V along the closed curve C. Okay, basically V dot ds. Okay, the Green's function says I take this line integral and change it into surface integral, so double integral. Now the interesting bit here, anyone tells us what's the interesting bit here? What's this? What's that? Vorticity, very good. So now the Green's theorem allows us to express this circulation suddenly in terms of something we're aware of. We know it's circulation, vorticity. So really, and it's an area over a surface, not over a line. So remember, we're going from a line integral to surface integral. So now, another way of defining circulation is to say, if I integrate my vorticity over a surface, that will give me my circulation. This is how circulation and vorticity are related. So it's the integral of vorticity over kind of a plane, if you like. So therefore, this circulation tells us the total amount of vorticity that passes through a plane or a surface in a flow field, which is very nice because now we can always, when we talk about circulation, try to link it to vorticity. So that's it really, the main concept of circulation. So yeah, if you think about vorticity being represented as small vortices rotating, okay, and you integrate all of those, you get what we call the combined strength of all vortices over a plane or surface. So that's just another way of saying that. But so the key thing is here, circulation is related to vorticity through a surface integral. Sorry guys, I have to go a little bit quicker. So let's just take a very simple example, which kind of illustrates some of the ideas I've been talking about within potential flow. So if someone gives you a stream function psi, which is just x times y, okay, the question is, find what the velocity potential phi is, and also show that phi and psi actually satisfy the Laplace equation. So how do we get about that? So now the given is that we know the stream function. So you start by saying, okay, first of all, we know that the partial derivative of psi with respect to x is y, just from here, and the partial derivative of psi with respect to y is x. But we know that u, remember we're trying to find phi, but we know that u can be written in terms of phi this way, but also is the same as d psi dy. And we know what d psi dy already is, just x. So I say d phi dx is equal to x. Again, I know that v in terms of phi is this way, and in terms of psi is minus d psi dx. But d psi dx is already y, and you just add the minus y. So really you end up with d phi dx equal x and d phi dy minus y. You can integrate. Okay, and you end up, I'm not going through the integral, it's quite simple, but you end up really, sorry. The main thing is understand what we're doing. Don't worry, you can do the maths later, I trust you. So you got two, because you got here d phi dy equal minus y, d phi dx equal x. So you got two equations you're integrating, you end up with two expressions for phi. The first one being this one, phi equal x squared over 2 plus a function of y plus k1, a constant, and from this one here you end up with phi. So basically you end up with two solutions for phi. What do you guys think this solution should be? You're saying phi equal to this, phi equal to that. What can you tell me about this term and that term? They are the same, yeah, very good. So I know phi equal to this side here, and phi is equal to that side, meaning, in fact, this side now equals to that side. So let's just equate those two sides for this to be true, well, because they're both equal to phi. And for that to be true, we just work out that this function is just minus y squared over 2, and hx is x squared over 2, and k1 and k2 are just the same constant k, for that to be the same phi. If you get stuck, ask me later. Okay, so we end up saying that really from the stream function that I started with, I now know what the velocity potential is. It's just written this way. So the next part is show that psi and phi satisfy the Laplace equation. So all you need to do is calculate the second order partial derivative of psi and phi and see if it's equal to 0. If that's the case, then it satisfies the Laplace equation. So you just do this and you actually get 0. Again, please do the maths on yourself. If you get stuck, ask me. If you do that with the psi, you also get 0. So indeed, phi and psi actually satisfy the Laplace equation, which is exactly what we want. So the flow is definitely potential flow. Okay. We can also calculate the vorticity, and because the flow is potential flow, your vorticity must be 0. So if you work out vorticity not with 0, obviously you've done something wrong. It means your flow is not potential. So this is just another check to make sure that vorticity indeed must be 0, and that's the case. So we end up with these functions psi and phi, okay? And actually, in reality, what it represents, I don't want you to worry about these. I will never ask you to plot horrible things like this. But really, what it represents is just flow from stagnation point, which actually this is just one corner, but in it could be something like that. So this is how the flow in a stagnation point might look like, okay? Which you can actually model by potential flow. That's the whole point. So here, for example, actually here I should label these. Here actually we're plotting the very blue lines, if you like. Are these, what's the color here? What's this color? What? Cyan, okay. So the cyan one is actually the velocity potential. The blue one is the stream function, which represents the streamlines themselves. Okay. What's the time? Gosh. All right. So, what's the application of potential flow? Why do we actually, or where can we use potential flow? Now it turns out, actually, even with these simplifications of potential flow being rotational, and then we can say we can also add incompressible, okay? Then there are actually applications where you can actually use this very simple model to model some interesting flows. For example, the flow around an aircraft, but there's something there. You can't actually model the flow around an aircraft very close to the surface, okay? Because there's the boundary layer. So potential flow, if you're employed by a company and they tell you calculate the flow around an aircraft, and you wrote your potential flow code and come back saying these are my results, and you haven't thought about the boundary layer, then that's not very good. So, but outside, very far from the boundary layer of the aircraft, it's actually quite a reasonable approximation. People use it for acoustics, water waves, things like that. So they're all really governed, can be modeled by potential flow. For us, of course, we care about aircraft. Now, the importance of potential flow, I can tell you in your CFD coursework, you're obviously using ANSYS CFX. ANSYS CFX is not a potential flow model. Is obviously based on the full Navier-Stokes equation, so it's a much more accurate model, which maybe you can ask me now, why do I care about potential flow? Well, that's the first thing. There are interesting flows that couldn't be modeled by potential flow. It's simpler to model. Okay, you don't need to do a lot of coding. The coding is simple if you create a code. But also, I think the historical impact of potential flow theory, because maybe in the 40s and 50s, all they had is those potential flow theory. They had to design aircraft based really on potential flow theory, and then based on engineering judgment, add other things. So it was actually quite challenging. They didn't have what we have today. But the fact that people were forced to write codes, very long codes in very complicated languages, and actually design aircraft with it, this led to this whole new development of codes for designing vehicles, including aircraft, and it's actually historically led to things like ANSYS Fluent and the rest of it, okay, which is based on the full equations. So historically, it has a very important place in history in terms of codes. But even today, believe it or not, someone like Boeing, and of course if Boeing is using something, then it must be useful. They're still using it in the transonic regime, believe it or not, and there is a code called TranAir. So they actually use it in the transonic regime to model flow around an aircraft. So we can use it also as a way to see the effectiveness of a design. So you can design an aircraft, run a potential flow around it, let's say transonic in this case, see what happens, maybe it's not what you're expecting, change the design and run it again. So it could be like a very first check on your design. So obviously the limitations, we know that potential flow does not exist in life, okay? This is very simplistic flow, but of course there are applications where you can use it. For what you definitely can't use potential flow is to predict the drag. Please don't use the potential flow to predict the drag, okay? If you take anything from this lecture, no. Okay? But we can actually use it to estimate lift. Lift is okay, but not the drag. So, other places where we can't really use potential flow is things like, as I said, boundary layers, wakes, because these are regions of a lot of vorticity. And remember, the whole assumption of potential, the main assumption in potential flow is the flow is rotational. Vorticity is 0. But these guys here, trading vortices with a lot of rotations, and flow separation with a lot of flow coming back from downstream, they're definitely regions of high vorticity. So we can't really use potential flow models for that. So just to summarize, yes, so potential flow. Typically, we're assuming that flow is rotational and inviscid. It satisfies the Laplace equation, and it's linear and harmonic. So we can create many solutions out of simpler solutions. And we said that circulation is related to vorticity, being basically the surface integral of vorticity. And in 2D, for incompressible flow, this is basically the conservation of mass written in velocity components. U and V can be written that way. And the vorticity formula in potential flow is dV dx minus du dy equal to that. And if it's potential, of course, this will be 0. So I think these are the key ideas